Last time we defined topological spaces. I showed you how to construct a topological space from a metric space. We discussed one example that wasn't of that form, namely the, which I claimed was not of that form, which is the Sierpinski space. And the last thing we checked was that if you take two metric spaces and turn them into topological spaces, then the notion of a continuous map is the same in both cases. Maybe I didn't phrase it quite that way, but that's what we proved. Okay, so, we also obviously defined continuous maps. Now, what I want to spend this lecture doing is teaching you how to construct topological spaces. So we know one method, which is to start with a metric space, and then of course we can sit down by hand and define topologies, but that's a really lame way to construct topological spaces. So what we're going to do is discuss the sort of most basic ways of building new topological spaces from old ones. That's products. I mean, you're all familiar with that one because you know how to talk about Rn as a product of n copies of R. Disjoint unions, or the fancier word for that is coproduct. That's sort of a dual construction to products. That's maybe less familiar. And we'll also discuss a notion which I'll call push-out, which is a form of gluing. So taking two topological spaces, identifying some part of them as being the same, and gluing them along that component. Okay, so using those methods, we'll be able to construct things like tori, the Mobius band, and other fun examples. All right, but to do all of that, we need to first discuss bases, because otherwise it's very laborious to describe, for example, the topology on the product. Well, although it may not be apparent at first sight, the concept of a basis is actually an equivalent way of defining what a topological space is. Instead of telling you what all the open sets are, I can tell you a kind of generating set of open sets, and I characterize what properties a generating set has to satisfy, and then it's actually an equivalent characterization / axiomatization of the notion of topological space, and indeed it's often used that way. So a basis for a topological space, so if I have a topological space Xt, a basis is a collection B of open sets such that for all pairs x comma u, where u is open and x is a point in u, there exists one of these distinguished open sets which lies inside U and contains X. All right? So whenever I give you a point in an open neighborhood, maybe I didn't define this term in the notes yet. So if I say an open neighborhood of a point, I just mean an open set which contains the point. Some references will use the word neighborhood to possibly mean a closed or an open set which contains a point. That is crazy, so we'll only use neighborhood to mean open, okay? So if I say neighborhood, I mean open neighborhood in the sense I just defined. Okay, so any open neighborhood of X contains a neighborhood which is in the basis. That's what that says. Okay. So some exercises. So B is a basis if and only if every U in T is a union of a subset of B. By union, I mean the union set, as I defined it last time. So take a subset of B, take the set of all elements which belong to one of the elements of that subset. Okay, so that's a union over a subset of B, if you like. Where I include the empty, anyway, so the empty union is the empty set. Okay, so that's another way of saying what a basis is. 2 Oh yeah, so this we actually sort of observed last time. So if B is a basis for the topology on Y, a function, so let X be a topological space, Y is another topological space, and B is a basis, then a function from X to Y is continuous. Well, to be continuous would mean that the inverse image of every open set is open, but every open set is a union of things from the basis, and inverse images commute with unions, so that's the same as saying that the inverse image of everything in the basis is open. All right, so check that. Okay, that's very helpful because often it's easier to describe a basis, and obviously it may be difficult if you have a very crazy topological space to sit down and check that the inverse image of everything is open. Usually you check it on a basis. Here's an observation which I didn't make last time but maybe is worth making. So if I have a function between two topological spaces, forget that you know about continuity from metric spaces. If you were just told that a mathematical structure of a topological space was a set together with some set of subsets, and you were asked which functions between sets preserve that structure, well, there's maybe two natural things you might try, right? One of them is you might say, the function is good if f of v is contained in ty whenever v is in tx. And there's only two ways to naturally compare subsets of x and subsets of y. You either take their image under f, okay, or option B would be that you say for all v in ty, f inverse v is in tx. Right? Those are the two possibilities that you could think of, right? Well, that's the one we take as continuity. Maybe it's worth mentioning why this doesn't make sense, right? Well, it's because, if I take a union of an arbitrary set of subsets, I always get the union of the images. That's also true here. Just if I take the inverse image of a union, I get the union over the inverse images. Okay, so from that point of view, both potential definitions, why do I care about this? Well, the definition of a topology is saying that it's closed on infinite unions. So I'd want this to work if this was going to be a map preserving the structure. And inverse images preserve finite intersections, which is why that's saying the inverse image of open sets is open is a reasonable notion of continuity, because both these things are true. But the image of an intersection is not necessarily that is not true in general, as you'll convince yourself if you think about it for a little bit. Okay, so that is why this is not a potential definition of continuity, and why, even if you didn't know about metric spaces, if you thought about it, you would write down this as the definition of continuity. It's the only thing that makes sense, given the definition of a topology. Okay, but that was sort of an aside. All right, so back to bases. If I have a metric space XD and I take the associated topology, the open balls where E and epsilon and X range over all points and over all all positive numbers respectively, they form a basis for the topology. That's by definition, basically, right? Or if you like, it was the second part of one of the lemmas I discussed last lecture. Okay, so that means that part 2 here is just recapturing the lemma from last time, that continuity was the same in both contexts, but in a more general sense. Okay, so let's prove something about bases. So the question is, if I have a set X and some collection of subsets, when is it the basis for some topology? Okay, well, here's the answer. So I need two conditions. Well, let's just work backwards from the definition. So suppose there was a topology on X for which capital B here was a basis. Well, then taking pairs of the form little x comma big X is open in itself, whatever the topology is, I must have an element of the basis which contains that element of X, right? So we must have at least that for each X in X, there exists B in B with X in B. Okay, and the second condition is maybe a little less obvious, but if I took two things in the basis, say B and B prime, and I took a point in the intersection, well, condition one would tell me there's some thing in the basis which contains that point. Well, I knew that already. There's two of them, in fact. But the idea of a basis is that it should be sort of as fine as you like, right? Every point should contain arbitrarily small things in the basis. That's the whole point of it, recovering the topology as a union. So I want to insist that there's something else in the basis which is contained in both B and B prime. Okay, so that's what 2 says. Given B and B prime in B and a point in the intersection, there exists B double prime in B with X in B double prime contained in B intersect B prime. Okay, so I mean that's clearly necessary because the intersection is open. Intersections are open in a topology, and then applying the definition again, I must have such a B double prime. So if it were a basis, it must satisfy 1 and 2, and now I claim that that is also sufficient. So if a set X and a set B of subset such, given a set X and a set B of subset such, blah, there is a unique topology T such that B is a basis for T. So let's dispense with the uniqueness first. So have a look at the first part of the exercise there. If I have a basis, then the open sets in my topology are precisely the unions of things in the basis. So there can only be one topology with a given basis because you can construct the topology from the basis. Okay, so the uniqueness is clear from the exercise. So I just have to prove existence. Well, again, by the exercise, there's only one potential topology, which is just to take unions over all the things in B, and then I hope that these conditions are enough to force that to be actually a topology. Right? Okay, so T is going to be all the subsets of X, such that for all X in V, there exists a B in B with X in B contained in V. Okay, that's just another way of saying V is a union of elements of capital B. Okay, so now I've got to prove the 3 axioms for that to check that it's actually a topology. Okay, so T1 says the empty set is in there. Well, that's vacuous because the for all doesn't apply to anything if V is empty, so that's true. If I take X Well, that's exactly what 1 says, right? For this to be true for v equals x, I'd need for all x in x, there exists a b in b with x in b, and that part is content-free. So that is exactly what 1 tells me. Okay, for 2, I need this set T to be closed under finite intersections. So given V1 and V2 in T, I need to show that V1 intersect V2 is in T. To do that, I need to take a point in V1 intersect V2. And I need to show there exists a B in B, which is contained in the intersection. Well, by definition, X is in V1. And so by definition, by this, there exists a B1 in B with X in B1 contained in V1. And similarly, a B2 with X in B2 contained in V2. Well, X is in B1 intersect B2. So by the second condition in this lemma, there must exist a B double prime. Whatever, let's call it B3. With X contained in B3 contained in B1 intersect B2. But, well, B1 is contained in V1 and B2 is contained in V2. So that's contained in V1 intersect V2. And so I'm done, right? I produced a thing in B containing X and contained in V1 intersect V2. So that checks T2. And then V3 is, there's really nothing to show for that. Let's see. Right, I set T up to be a union of all the things in B. So then if I start taking unions, of course, it's still a union of things in B, right? So that's why there's nothing really to show for part 3. Okay, so let's just write that down. So given a collection of sets which belong to T and an element of the union, well, we need to prove the union also belongs to T. So given an arbitrary element, I've got to produce a B which contains it and which is contained in the union. Well, to be in the union is to say precisely that X belongs to at least one of them, right? Then since that VI0 belongs to T, there must be a B with X contained in B, contained in VI0, but then that's contained in the union. And so I'm done. I produced a B, and X is in B, and B is in the union. So that's it. Okay, so that's it for the lemma. So we say the topology T is generated by the basis. In the same sense, an abelian group is generated by generators or a module or anything else. It's the same idea. Any questions about that one? All right, so that's a convenient way to set up topological spaces, to give a set, to give a basis, check the thing is a basis. Well, sometimes you'll see in references people call a collection of subsets satisfying 1 and 2 a synthetic basis, merely because before you wrote down T, it wasn't really a basis for anything. It's just a collection of sets with some condition. But if I say a set of subsets is a basis, without conditioning that on, is a basis for this topology, what I mean is that collection of subsets is a basis for some topology, which is precisely to say that 1 and 2 are true. Okay, so if I say a collection of sets is a basis, or check that it is a basis, I mean check 1 and 2 there. All right. Okay, so perhaps the most important way of constructing topological spaces is the product. And as I mentioned earlier, that's the first construction you ever really see when you think about spaces, right? Rn as a product, Cartesian product of copies of R. So if we have a possibly infinite family of topological spaces, well, the Cartesian product, which I denote with this capital pi, indexed by the index set I. I wrote down in the notes like what set theoretically the product is, if you haven't thought about this. It's actually functions from the index set I into the disjoint union over all the xi's, if you want to be pedantic about it. But usually you're just happy thinking about sequences or indexed families of elements, right? And that's fine. Okay, so the infinite Cartesian product is sequences indexed by I, where each xi is in xi. Is a topological space. Where the basis Okay, so what's a basis? Well, take an open subset of each xi, call it ui. So that's potentially an infinite number of open subsets, indexed by I. Then take their Cartesian product, that sits as a subset here, right? That's just the xi's, where xi is in ui for all I. Well, for any collection of open subsets, that is a subset. But I don't take that as my basis, all right? You'll see why in a moment. I take as my basis such products, but where almost all of those UIs are just the whole thing, xi, and there's finitely many exceptions, right? So if you want to think about I as being the natural numbers, it's sort of like it's always the x's, and then suddenly at some integer, there's some finite range where I take something else. But outside of that, I'm just taking the Cartesian product of the whole space with everything else. Now, if I'm taking a finite index set I, you don't need to worry about this, because it's always true if I is finite, but it's worth... we're going to talk about infinite dimensional spaces later, right? Sequence spaces and such things. They will be infinite Cartesian products. Okay, it's a topological space with bases consisting of sets of the form such. Okay, so the question is that a basis? Does it satisfy those conditions? I've left that as an exercise, okay? So just check those two conditions for that collection of subsets. Well, you might wonder why set things up this way. I mean, if there's a finite number of things, we'll just write it down in the usual way, right? X cross Y cross Z, for instance. I mean, the reason is just to avoid some sort of niggling issue, which I like to use to scare my first year calculus students, which is, you know, what is R3? Is it really, you know, is it R cross R cross R? Or is it R cross R cross R? Well, those are not the same set, right? I mean, the first case, they're sets whose first component is a pair, and the other case, they're sets whose second component is a pair, so they're not the same sets. I mean, they're not literally the same topological spaces either, right? But who cares, right? That's kind of a meaningless thing to worry about. The point is that R3 is neither of those, right? R3 is functions from a 3-point index set into R. So that is the right way to define R3, not by choosing some way of breaking it up into factors. That's nuts, okay? So that we never have to think about this, we have a definition where I just take an index set and I take a product over the entire index set. So that's the sane way to set things up. All right. Okay, so I'm going to discuss the properties of this topological space in a second. But before I do, well, actually maybe a discussion of homeomorphisms can wait until next lecture. So let's discuss what's called the universal property of the product. Who here took Nora Ganter's algebra class? I know some of you. Oh, just one of you. Okay, well. So the words universal property, if you've ever taken a class with Nora, you will have seen, and you will see when you do. Anyway, so what's a universal property? Well, it's a way of talking about a mathematical object, in this case a topological space, in terms of what it does rather than sort of what it is in a set theoretic sense. Okay, none of that will make much sense to you right now, but when you've seen the following statement, you'll get what I mean. Okay. It's a lemma. So given spaces, and whenever I say space, I'm going to mean topological space from now on. So given spaces xi and y, there is a bijection between the following two sets. So the first is continuous maps from y into the product. And the second is the product, just as a Cartesian product of sets, of continuous maps from y into each xi. Okay, so the fact that it's a bijection we'll think about, but there's only one reasonable way of defining this function, right? Which is to send an f. So that's a continuous map from y to this product with the topology we've just given to it, to the sequence, which is the projection followed, well, after f for each I, where pi I maybe that's bad. I hope it's clear what I mean by projection. Right, take the Cartesian product, that's sequences, and just read off the jth entry of the sequence. That gives you a map from the product to any given xj. Exercise, check that map is continuous. Okay, actually, the inverse image of an open set here is in the basis already, if you think about it, right? So it must be open. Okay, so if I take F and then I compose with any given projection, I get some map, and take all those maps together, and that gives me a sequence, I-index sequence of continuous maps. Okay, so I claim that's a bijection. Well, before I prove it, why would you care about that? Well, it's because checking that a map into Rn is continuous can be a bit laborious if you try and use a metric, right? I mean, okay, so Rn, we now have two ways of defining that a priori as a topological space, right? One is to take the metric and take the associated topology. That's one version of Rn. And then we've got another version where we just take the Cartesian product of n copies of R as a topological space, according to this definition, right? Exercise, check that the topology you get on Rn from the metric is actually the same as the product topology, okay? So Rn, as we've set it up last lecture, is exactly a product of n copies of R. What that means that continuous maps into Rn are in bijection with a sequence of continuous maps into R. All right? And that's what you want to be working with. You don't want to be thinking about metric distance in Rn if you're trying to check that a map into Rn is continuous. You want to say a map into Rn is continuous only if its components are all continuous. Right? That's a statement you're probably familiar with from real analysis. Okay, so that's the kind of reason why we want this statement. It means that we can really understand continuous maps into a product working component by component, and that is a sane thing to do. Okay, so, well, I've defined a map. We have to prove that it's a bijection. Well, maybe let's observe it's well defined first. So if f is continuous, then pi I circle f, that's a composite of continuous functions, so it's continuous. So that means, let's call this phi. That means phi is well defined. Well, maybe let's deal with injectivity first. I mean, why is phi injective? Anybody? Actually, this has got nothing to do with topology, right? I mean, continuous functions are functions with some property, but if I tell you I've got some function into the Cartesian product, I mean, forget about the topology. That means for every y, I've got a sequence of things, and I'm telling you, I mean, if phi f and phi g are the same, then in each position they put the same thing for every y, right? So they must be the same functions. So, if phi f equals phi g, then for all y and y, we have y and y and j, y and I. F, y, right? So evaluate f on y, that gives me a sequence of things in the xi's, right? Let's take the ith term in that sequence, so to speak. But that is exactly pi I circle f of y, right? That's what the projection does. But pi I circle f is the function which lives in the ith coordinate So phi f is some sequence of functions, and that's the thing in the ith position. So if I take now that phi g and phi f are the same, I'll just keep going. So f equals g. All right. So that really had nothing to do with topology. That was just the nature of the Cartesian product. Okay, so phi equals f, and f equals g, sorry, and so phi is injective. Okay, so let's do surjectivity. That's more interesting. Okay, so to prove it's surjective, we need to suppose we're given something on the right-hand side. So that is, given a family of continuous maps. Let's call them Fi. We need to construct a continuous map from Y to the Cartesian product with those components. Well, I mean, what the map has to be if it is continuous is clear. The question is whether it's continuous or not. Right? So we define a function, not necessarily continuous yet, we don't know, from y to the Cartesian product. Well, just by sending a y we evaluate all the fi's, and then we accumulate to get an element of the Cartesian product. So if we can show f is continuous, clearly then phi f has to be the sequence we started with, right? Because we set it up so that the components of the f are the fi's. So if f is continuous and lives in the left-hand side, it does map to the sequence we started with. And therefore phi will be surjective. So we just need to show that this f is continuous. Well, I mentioned earlier that if you have a function into a topological space for which you know a basis, to check that that map is continuous, you just need to check the inverse image of a basis is open. Okay, and well, we have a basis for the product. Whereby as above, I mean if the UIs are open in xi and only finitely many are different from xi, we need to prove that f inverse of that Cartesian product and then we need to check that's open. Okay, but let's just write down what that is. So that is all the y's in y such that fy is in the product. But that's all the y's. I mean, f of y by definition is that sequence, right? F of iy. Well, that's something I can check position by position in the sequence, right? So that will be all those y's such that fiy is in ui for all I in I. Okay, so now if you think about the next step, you'll see why we took this condition on the sort of finite support of the sequence. right? Because what's another way of writing this? This is an infinite intersection. Right? That intersection is precisely all the y's which belong to all the inverse images of all the ui's. Right? Now, infinite intersections of open sets are not necessarily open, but that's not really an infinite intersection. Right? Because if we have some uj equal to xj, then that term in the intersection will just be the inverse image of everything, which is y. And if I have a big intersection and there's a y in it somewhere, well, y intersect with anything doesn't do anything, so I can just leave those out of the intersection, right? So that's just the intersection over all the i's for which ui is not equal to the whole thing. But that's finite by definition of the basis, so that's a finite intersection of open sets, which is open. Okay, so I proved that f was continuous, and phi of f is clearly the sequence I started with, so that proves that phi is a bijection, and we're done. Okay. Any questions about the proof there? Okay, well that's good feedback, thanks. All right. Okay, so that was too fast, I guess.
Okay, so the real question is, I'm starting to lose track between, I lost track a little bit of what was the projection map and what was the product?
What was the projection map and what was the product? Oh.
Like which pies?
They look very similar, that's quite fair, yeah, okay.
I think I got it sorted out.
Yeah, maybe I should be a bit more exaggerated with the pies, yeah. Or maybe even use different letters. J. Yeah. Okay. So starting from the product, we have the map. Maybe I'll write down what this is as a function, right? So pi j of a sequence just reads off the jth element. So first we check that's a continuous map. And then that means that function is well defined, and then it's just a question of proving it's a bijection. Yeah, okay, well, perhaps that was a bit fast, but there's no point repeating it, I guess. Okay, maybe the best thing for me to do is to just reflect a little on this case. I mean, so by this I mean give this the topology induced by the D2 metric, and by this I mean the topological space I've just defined. Okay, so let me draw some pictures which sort of give you a taste for what the bases look like. Well, in R2 with the metric topology, as we've discussed, the basis is given by the open balls, right? Okay, so you vary x, you vary epsilon, that gives you all the elements of the basis. So that's what this topology is talking about. If I took the metric topology on R, so that gives R the structure of a topological space, and then I applied this construction to get the product topology. Maybe I should have said so. So this is called the product topology. So what is that doing? Well, I mean, it says take an arbitrary open subset of each component. The business with finitely many is irrelevant because there's only finitely many things in the index set. So just take a U1 in the first copy of R, so to speak, and a U2 in the second copy of R, and then take U1 cross U2 as a subset of R cross R, and that will be something in my basis. Well, I can be a little more economical because I just need to take all the things in a basis for R, so I might as well just take the intervals between A and B, right? So let's instead think about AB, CD. So an element of my basis for the topology, by definition, will be that guy there, which, I mean, if that's A, that's B, that's C, that's D. I mean, that's this sort of fuzzy rectangle that's missing the edges, right? So that's that set there. It's not quite what the statement says, but this collection is also a basis. If I take A, B, C, and D arbitrary, that's not that basis because there I'm taking arbitrary open sets, but this is also a basis if you think about it. Okay, so why do these give rise to the same topology? Right, it's sort of, right, I can always squish a rectangle inside a circle and squish a circle inside a rectangle, right? So it's sort of intuitively clear that they should be the same. Because, okay, to prove that this set is open in that topology, what do I have to do? Well, I have to prove that given any point in here, I can find an element of that basis which is containing that point and contained in the rectangle. Well, that's clear. I can just take the circle sufficiently small and I'm okay. Right? And similarly over here, why is this set open in that topology? Well, given any element of the circle, I can find interval sufficiently small which fits inside the circle. Okay? So those are two different bases which generate the same topology. Okay? And the exercise, or maybe I didn't say it out loud, but there's an exercise in the notes to check that Rn is the same topology, if you get it from the metric, as taking an n-fold product of R with itself. And it's just the same reason, just in n dimensions. Okay. So, well, what's wrong with this way of doing things? I mean, nothing. That's a perfectly good way of setting up the topology. But it's not very useful, because if you want to check a map into R2 is continuous, you have to think about balls all the time. And the way this is set up, it's not obviously component by component, right? I mean, an open ball is not the Cartesian product of two things. So it's not set up in a way that's designed for you to work component by component. Whereas this topology, I mean, this is the same topology, but this basis is set up so that you can reason about the continuous maps into that component by component. And that's what this is saying, right? And that's, you know, how we're going to use the product topology. Okay, so wait. Yeah, that's it. Okay, so we'll stop there for today.